lecture. In this particular lecture, we're going to consider one-dimensional random walks. In the last lecture, we had considered Monte Carlo simulations in which we were generating a certain state of the entire event. So we were not necessarily taking the entire process into considerations. We just were worrying about how the final state looks like. But in this particular lecture, we're going to look at the process in particular. So let us begin by the very simple process that is going to be a set of particles which are originally located at the origin. Okay, so there are a bunch of particles all stacked on top of each other. Well, it doesn't matter whether they're stacked or not, but we have, say, a lot of particles at the origin. Then at the next time instant, there is we sample a step. Okay, so for each particle there is a step. It can be either -1 or it can be +1. And so the point is, depending on whether the sampled step is -1 or 0.1, we will either move the particle to this side or this side. And we'll do this for all the particles. So this sampling is different for each particle. But we are necessarily sampling from either this or this. So this kind of sampling is called as the binomial sampling or the Bernoulli trial. So this particle, suppose it gets over here, this particle also gets over here, this particle gets over here, this particle may get over here, and so on. Then over the next time instant again, you find out what step increment it must have by sampling from this. And you keep doing this. And the question is, for large times, how does this particular, so let me call this as particle in number. So particle number 0, 1, 2, and so on. And this is delta x at some time. So maybe we will have x0, x1. So these are all at some final time t. So we are interested to know what is the distribution of all the locations of all the particles at the final time. Whether all the, so if the distribution of the final location looks something like this, it means that all the particles are sort of accumulated over here. If the distribution looks something like this, then we can say that the majority of the particles, so this is what the PDF is, the PDF of the final location, the probability density function. So the probability density function having a high value over here means there's a higher probability that the particle is inside this range and a lower probability that the particle is either too far from this mean or too away from this mean. So the question is, how can we perform this particular random walk? Okay, this kind of process, it's a random walk, and what can we infer from it? In general, random walks are not just some synthetic simulations like this, but they often have a very deep physical understanding for various processes occurring in nature and for various engineering and science applications as well. Okay, so that notwithstanding, let us begin. So let us go over here. I've already pasted this particular bit of text that we will need. All right, so now let me just, yeah. So what we need is to sample from a given distribution. Okay, so there are various functions available inside NumPy which can help us do that. So let me first create a function, okay, which will help me obtain various steps. Okay, so let me define a function called as getSteps, and the input will be n, that is the n over here. I would pass it as the number of particles. So if all the particles are like this. So there are n number of particles. So I will ask the computer to give me n number of such increments, and they would necessarily be sampled from this. Either it will be +1 or it will be -1. Okay, so fine, and I must return np.random.rand int between 0 and 1 plus 1, because randint does not include the end number. So this is the end number, this is the number I want, and +1 is because I have to increment the range by 1. It excludes the outer range. Okay, and I must give size equal to n comma. So it's a one-dimensional array of size n. So this is how I have the definition of this. So in fact, let me show you how we can do that. So let me say s equal to get steps 10. So let me now print what s is. So it's sampling between 0 and 1. Yeah, that's what we see. So now I want to sample between -1 and 1. So I will multiply this by 2 and subtract 1. Okay, so let me run this. So now you have a bunch of numbers, or an array of size n, here in this case 10, which are comprised of 1 and -1. Okay, so now let us go into the other part of the logic. So we have to now initialize. So we have to declare how many particles we have, we have to declare how many time steps we need to have, and so on. So let us define np as the number of particles as, say, 10,000. Yeah, well, this is not 10,000, this is 100,000 or 1 lakh. Let me define the number of time steps. Let me put it on one line. So number of time steps, let's say it's 100. So now what do? We will initialize all the particle locations. So we want to vectorize the program. You can do the following. You can do the following pseudocode. For I equal to, I mean, this is just a pseudocode, it's not Python code. 1 to number of particles. Okay, for j equal to 1 to time steps, so n time, meaning I am grabbing hold of one particle in a loop, and I am sort of iterating in time to find out the new location of the particle. So x j plus 1 would be xj plus delta x for that particle. I can do this, right? So it's like for each particle I have to do these many number of operations, so the complexity would be n particle multiplied by number of times. So that's rather expensive, but in Python we know that we can sort of vectorize everything. We can do all of this without having to write this double loop. In fact, we can do a lot of things without having to write loops, and that's the part where you achieve speed. Okay, in C there is no option to do that, but in Python that is what exactly you are aiming for. So we will make a matrix X which will be something like this. So at a given delta t, so this will be delta t equal to 0, not delta t equal to 0, this will be t equal to 0, and these will all be the particle locations. So we must create a matrix whose number of rows will be n part and whose number of columns will be n time. This will be t equal to delta t equal to 2 delta t, and so on. So for a given row inside this matrix, we would essentially be singling out one particle and having its positions at all times. If we look at a column in this matrix, we are freezing time and looking at the positions of all the particles at that given time. Okay, I hope this much is clear. This is essential to understand in what is going to follow. So x will be np dot zeros, and the size, so here it will be np nt. All right, so far so good. and n. So we must also we have already initialized x to be 0. I mean, the fact that the simulation must start so that all the points are initially at x equal to 0, that is already satisfied through this statement. Now what we must do, I'm gonna make one loop over here for I in np dot a range 1 comma nt, meaning for I going from 1 to nt minus 1, right? Because I equal to 0 is already the initial condition and that we already have. Inside this loop, what I'm going to do is xi equal to x, well, x all rows of the ith column will be x all rows of the I minus 1th column plus steps, alright? So essentially it is saying that all these rows will be all these previous locations plus some step, right? And the step is simply sampled from the function that we have defined above. All right, so now steps will be get steps, and here it will be np. All right, so with this particular loop, what we can do is we can simply, yeah, once this loop completely runs, we can have a look at the trajectories. So how do we do that? We will do plt.plot and we will simply plot. So let me create a time loop or a time array ta np.linspace np.a range 0 comma nt, and correspondingly we have all the locations. So we want to plot, suppose I want to plot the trajectory of the particle with index equal to 0. That means this first row, all the points correspond to all the locations at successive times corresponding to particle with index equal to 0. So let's do that. So we'll do ta comma x 0 comma all, right? So let's do this. Let me just suppress this. Okay, so it starts with 0, then it does this walk. So some increment, some decrement, some decrement, increment, and it keeps on going like this. Okay, no problem. In fact, if I run this again, it will create another plot. The reason why it will create another plot, because I would be resampling the random numbers, I would be resampling the steps the particle would take. Okay, so once I do this, I get another trajectory. So in fact, we can loop over some numbers and plot certain trajectories or sets of trajectories. So for j in np dot a range, let's do 1 to 10, let's plot these trajectories, and then I'll put this inside the for loop and I'll put j over here. So this should give me all the trajectories. So there you go, these are the various trajectories. So what is the x-axis? So plt.x label, so x-axis is simply time, whereas the y-axis is nothing but the location, right? Okay, so these are the evolution of the locations of the different particles in time. Okay, so what are we interested in? We're interested in finding out the distribution of locations for such a system. Meaning, I will freeze time, I will look at all the locations, and I will try to form a histogram. In fact, let me put down a few more trajectories and we can copy it. And so let me take this to our notebook. So we will fix time and look at the locations of all the particles. Okay, we have a bunch of particles. So what do we have? We have some particles which are at 17, some which are, so majority of them appear to lie near the origin. There are some outliers and so on. Then what we will do is we would like to find out the PDF, the probability density function of the location at some later time t. Because they are more clustered near the origin, we expect a distribution something like this, where this is x equal to 0. And why do we expect them to be clustered? Because you see the distribution from which the step is sampled, it's either +1 or it's -1. Meaning, if it goes +1 in the positive x direction, it's equally likely in the next time instant to come back to -1. Okay, so that's why you will see more clustering near x equal to 0. But what is the nature of the distribution? That is what we are more interested in. Okay, so let's do the histogram. So this basic program, we have all the trajectories, but we are more interested in the histogram of x at a given time. Okay, so this is how the update happens. So far so good. Let me split this so that it's in a different cell. We don't need this at the moment. So what should we do? So suppose every 10th step I plot what the histograms are. Okay, fine. If np dot mod I comma 10 equal to 0, meaning each time I is a multiple of 10, we will execute something inside this. So what will we do? So we will first say all the samples from which we want to create the histogram. Look, again, I'm gonna repeat. So we are gonna freeze time and look over all the locations that we have for different particles. What that means is we're gonna look at a certain column at a given time. This could be, for example, t equal to 10 delta t. Then we'd do the same for t equal to 20 delta t. So we'd look at all the locations and try to plot the probability density function, right? So s equal to x I comma all. This means it now contains all the locations. So this I call as s for samples. Now I will create a bin space. So in order to create the histogram, I must tell what the bins of the histogram should be, so that the program can assign those many counts inside a given bin. So bin space, I just want to call it bin space. You can call it anything you want. So this will be np.arange, and it will be going from, so what should be the decision how to find out the bin space? Look, in at this particular time, I know that the maximum value is something like 17. The minimum value is something like, I don't know, at this point of time, it's something like -50. But whatever. So we have to make bins going from 15 to 17. So it will look something like this. So -15 to 17, and I must create a bunch of bins. And each time a particle location lies in a bin, I will make the counter +1, +1, +1, +1, and so on. There will be fewer +1s at the edges because of the discussion we did few moments earlier, that the clustering will be near the origin. So in that case, if I ask the computer to, instead of giving me the count, give me the density. So because it's an important aspect, instead of giving us the count, it will give me the density, meaning it will normalize everything by the number of particles. So if I have n counts over here, I will divide it simply by n to get the density. So I will do this. So the space over which I want to plot the histogram must be appropriately defined. If you don't define that, Python will assume a certain number of bins and do the calculations. You can always override it. Okay. So I will have it going from np.min of s to np.max of s. And I will take the step size to be 2. Why have I taken the step size to be 2? Let's see. So this is 0, this is 1, this is minus 1, minus 2, 2. So after one time step, particle will be either at minus 1 or it will be at plus 1. So at delta t, the particles are at odd locations. At the next time step, it will either go to 0, it will go to 2, or it will go to 0, or it will go to minus 2. So at 2 delta t, the particles will be at even locations. So that is why, in order to avoid the seeming dichotomy occurring in this problem, I'll just simply take bins of size 2. Okay, I'll simply do binning of size 2 rather than doing a bin of size 1, because I'll show you, if you do a bin of size 1, you will get empty peaks for every interval. Either if you have odd time, then you will have empty even bins. If you have even time, you will have empty odd bins because of this particular logic. But this is not of great concern because I'll choose the bin size to be 2.0. Right. So now that we have defined the bins, now that we have the samples, we will call the histogram function. So it will be counts comma bins equal to np.histogram s comma bins equal to bin space comma density equal to true. All right. So the np.histogram command takes as an input the sample, the bin space, and whether density has to be true or not. It will give as an output the counts. So if density is false, it will give you the actual integer count. If the density is true, it will give you the fraction. So essentially it will give us a normalized count. And bins will be the same as bin space, but no worries with that. Alright, so this is what we have. Then what should we do? We have to plot this. So plt dot plot. So the thing about histogram is it will, so these are the edges of bins. So this will be bins 0, this will be bins 1, bins 2, 3, 4, 5. But counts will be 1, 2, 3, 4, 5. Rather, this will be count 0, count 1, count 2, count 3, count 4. So the number of elements in the array counts will be 1 less than the number of elements in the array bins. And that is just something because of the edges and the center value. So what we'll do, we'll disregard all that. We'll simply do a plot of bins 0 to minus 1 comma count. So I'm sort of shifting everything to the first element. What I'm doing is whatever this is the value, I'll associate it with this edge. This value I'm associating with this edge. This value I'm associating with this edge. This value associating with this edge. This value associating with this edge. This value remains empty. And how do I choose 0 to second last element? It's through this command. As simple as that. We've done this iris splicing in the very beginning. So if you've forgotten, just make a random array and try to do the splicing and see. All right. So let's run this and see what happens. Okay, we have something weird going on. So why is that? Ah, so a very critical mistake we have made is sxi comma all. This should be, so essentially we're trying to get all of this, and this is x all rows of the ith column. So rather than this, it has to be, well, in the heat of the moment I might have written it reverse. Anyway, no harm done. What did I do? Yeah. Okay, great. So this is how the evolution of the probability density function looks like. In fact, let me give it the labels over here. So plt dot x level, this is simply going to be x. Plt dot y level, it's simply going to be p of x. And plt dot title, probability density function of locations. All right, so what do we see? We see that initially everything is peaked about 0, and still everything is still peaked about 0, but as time progresses the PDF sort of flattens out, it widens out. And let me increase the number of time, or let me do this and let me take a plot every, yeah. So this is how the evolution happens. The PDF peak becomes smaller. So what is the meaning of the fact that the PDF peak becomes smaller? So let us plot this over here. So what is the difference between this PDF and this PDF? This PDF means, so on the x-axis we have x, on the y-axis we have p of x. That is the probability density function of x. So in this PDF, what it implies is these are the most likely values that you're going to encounter because of this distribution. And these are the highly probable values. But when the probability becomes something like this, so in this particular PDF, you would not expect values of x over here because the probability is going to 0 over there. But in this particular flat PDF, the probability of finding a value over here and over here is not that different because it's a very flat PDF. In fact, a uniform PDF looks something like this. This is x, this is p of x. So this is how the PDF for a uniform distribution looks like. It is equally likely for this value and this value to occur. In fact, for any value to occur. Okay. So the pointier the PDF, it is more likely to fetch you values near the pointy location. The flatter the PDF is, it's more likely to get you a range of values in that flat location. Okay. So, but still, regardless of that, it is seen that the locations near the origin are more likely to come than locations away from the origin. Okay, and all this is a consequence of the central limit theorem, which means which says that if you have a process in which you are sampling steps from a distribution which has a finite variance, then you're gonna end up with a distribution of locations which is described by the normal distribution. Okay, so in this particular case, we are sampling the steps from a very simple distribution. It's a binary distribution. It's either 1 or -1. So the variance of this distribution is bounded, meaning in this particular distribution, you have a well-defined mean, the mean is 0, and you have a variance as well. You can easily find that out. So given this distribution, which has a finite variance, you're going to end up with a distribution which is a normal distribution. A normal distribution is also the name of a Gaussian. So now if we chose any other distribution which has a finite variance, would we still get this? That is the question. In order to find that out, let us copy this code. Let us get rid of these trajectories. We don't need the trajectories of now, as of now. Let me sample from a uniform distribution. And the uniform distribution goes from -1 to 1, right? And let us run this also. Let's see what happens. And again, we do get a normal distribution. So I'm saying a normal distribution, but how do you know it's a normal distribution? For all you know, it's not a normal distribution. Okay, we'll show how we can figure out it's a normal distribution or not. For now, you just take my word, it's a normal distribution. So what can we do now? We've shown that given any distribution, it converges to the normal distribution. The key point is that the distribution from which we sample the step size, it has to be bounded, meaning it has to have a finite variance. If it doesn't have a finite variance, then it will not converge to the central converge to the normal distribution. It will not follow the central limit theorem. In that case, we have to generalize the central limit theorem to find out what it does converge to. But through this very simple program, I've shown you how you can find out such kinds of simple random walks. Now, let us take this a step forward and let us try to find out the mean and the variance for all the different look all the different distributions that we have. So now, given so we don't want to, okay, let me copy this function again. Let us go to a new cell, and in this cell we will try to find out the variance and the mean of this evolving distribution. So let me get rid of these plots. So what we have is the distribution. What is the distribution? It's a function of bins and counts. Okay, so in order to find out the mean, so let me call the mean as m. It will be simply the integral of, so what is the mean? Let me write down the definition. So the mean of x is integral x of fx dx, or p of x dx. So the x over here is bins and the f of x is the counts. So np dot traps over here it will be, so we're trying to find out bins 0 to -1 times counts, comma, bins 0 to -1, because the syntax for finding out the integration by trapezoidal rule is that you must have y first and then x. So this gives us the evolution of the mean. Now once we have the evolution of the mean, let us have the evolution of the variance. So the variance will be np dot traps. So now this will be something comma bins 0 to -1. That something will be multiplied by the PDF. The PDF is the counts in this case, and over here we will have bins 0 to -1 minus the mean squared. So essentially what we're doing is the variance will be integral x minus mean whole squared of f of x dx. So just verify this is the same as this. All right. So now that we have expressions for the mean and the variance, let us do a plot of these. So plt dot plot. So we'll simply do a plot of I comma m. Okay, and label equals. This is gonna be mean. We'll do plt dot plot I comma var s r label equal to variance. So let me run this. There appears to be an error. Too many. This has to be comma. This has to be a colon. Okay. So what do we see? Let me do plt dot legend. Oops, we have too many legends. All right. Anyway, it's using each level every time. But anyway, so the variance is the square red marker. It increases linearly in time. So how do we know it's linear in time? We will plot the linear function as well, whereas the mean is always hovering near 0. Okay, so on top of this, let us plot a linear trend line as well. Okay, so let me do TA again is going to be np dot arrange 0 to nt plt dot plot ta comma ta. Let me plot this as, so this is just to give a trend line. So this is a linear trend line. Okay, so the variance is having a different slope than y equal to x line. But let me put the aspect ratio of the plot proper. So ax equal to plt dot gca, ax dot set aspect to 1. Okay, so with the help of this, now we can ascertain what the slope has to be. Well, mm, the variance of the uniform distribution. Okay, let me first show you what happens when the distribution is same Bernoulli trial as the first problem that we saw. Then we'll look at the uniform distribution, and there is a small subtlety which gives rise to the difference in the slope. Let me run this. Boom, everything lies on the straight line, and this does mean that the variance goes as time, or the number of time steps. So this is called as a diffusive process. So in a diffusion process, the RMS distance goes as time. Well, the distance goes as square root of time. But anyway, if you take a square root of this, it's like an RMS is going as square root of time. So the point I'm trying to make is, in this particular case, the variance is 1. But in the uniform distribution, the variance is not 1, and that gave rise to a different slope. So now you may ask the question, wait, what is the then variance of this uniform distribution? What is the variance of this uniform distribution? So let us find it out. So if you have a uniform distribution between A and B, the distribution will look something like this. So we know that p of x dx integrated from a to b has to be 1. This implies that p of x has to be necessarily 1 by b minus a. So this is how we define a uniform distribution. So what is the variance of the uniform distribution? It's gonna be integral x square p of x dx going from a to b. So this is going to be integral a to b x square 1 by b minus a dx. So it's going to be 1/3 times b cube minus a cube by b minus a. This is going to be 1/3 b square plus a square plus ab. So b minus a cancels out from the numerator and denominator. So now if b is equal to minus a, that is for a symmetric distribution, what do we have? 1/3 2b square minus b square. So it's essentially b square by 3. If we require the variance to be 1, then what do we have? Over here we will have b has to be square root of 3. Rather, the uniform distribution has to sample from plus minus square root of 3. Alright, so let me now run this and see whether we get something. Boom, we get the same trend line. If I choose this to be something else, I'll have a different slope. Right? So now this is how you can now do many numerical experiments. You can choose a wide range of different step size distributions. So far we've focused on step sizes which are not step sizes but steps which are bounded. But what happens when, by bounded I mean when the variance exists, it's not undefined. But we can have the case where the sampling of the step size is from a distribution which does not have a variance. When can that happen? Let's look at the definition of variance in that case. So we have something which is something like this. Now the variance may not exist for a wide variety of distributions, and in general a power law distribution. The most uh, common distribution that is used is the Pareto distribution. So Pareto distribution has a power law tail something like this, and it ranges from m to infinity. So a Pareto distribution, the variable lies between m to infinity, and it has a form p of x is m a to the power, or rather a m to the power a upon x raised to a plus 1. Yeah. So now let us see what is the condition with the mean. So the mean of x would be integral x p of x dx going from m to infinity. And so this is going to be a m to the power a 1 over x to the power a dx. So this is a, so this goes from m to infinity, a m to the power a, so x raised to minus a plus 1, so x raised to minus a plus 1 upon minus a plus 1. This goes from m to infinity. So now if the limit at infinity has to exist, then minus a plus 1 should be less than 0, which implies that a has to be larger than 1. So if given this distribution, if a is larger than 1, then the mean exists. Now with the similar logic, you can clearly see where we're going with this. When does the variance not exist? Okay, so let us do that. So integral x square times the distribution a m to the power a 1 by x to the power a plus 1 dx. So what is this going to be? A m to the power a 1 over x to the power a minus 1 dx. So this. So now this is going to be x to the power 1 minus a. So this is going to be 2 minus a upon 2 minus a m to infinity times the constant. So this expression simplifies to this. Now this a m to the power a by 2 minus a x raised to 2 minus a limit m and infinity. Now this is going to exist when 2 minus a is going to be less than 0. And the reason I'm saying that 2 minus a has to be less than 0 is because the limit at infinity has to be non-divergent. If 2 minus a is greater than 0, then x to the power something greater than 0 will be infinity at infinity. But if 2 minus a is less than 0, then the large number raised to this exponent which is less than 0, that will decay, that will become 0. So the bound at infinity will be well behaved, and that gives rise to this kind of constraint. This implies a greater than 2. So we can see that if a belongs to 1 to 2, then the distribution has a finite mean, but the variance is not defined. In that particular case, does the distribution converge to uh, a normal distribution or not? That is the question. And the answer is obviously not. But how does the distribution look like? So let me grab this real quick. Let me go over here. And instead of this, let us get a Pareto distribution. So you must return np.random.pareto. And the parameters for the Pareto distribution are a comma size. Okay, so it will be a comma size equal to n comma, and it has, we have to add 1 for giving the scale factor and multiply everything by n. All right, so this must now also accept a comma n. Right, no problem. So now while calling the steps, I must also pass, so let a be 1.2 and let n be 1. But now what is going on? It's a one-sided distribution, meaning that, okay, before all that, let me show you how a Pareto distribution looks like. Um, then 100,000 comma 1.2 comma 1. So now let me do a histogram of S. So counts comma bins comma nothing equal to np dot hist S bins equal to 100. Oops. Sorry, plt dot hist. Um, okay, so I've taken only a linspace between 1 to 10 just to show you how the density looks like. So it looks something like this, meaning it's more likely for you to sample around values near 1, and the probability for higher values of x goes down, but it is not really 0. Okay, it lacks a variance, meaning it is not bounded to some number. It is always sort of falling down. So in a log-log plot, it will look like a straight curve. Let us see. There you go. So it's continuously falling down. It's not really falling off very sharply. This is in contrast to a normal distribution or any bounded distribution where you do this, you will have a sharp fall. And this will be quite apparent at the end of this particular exercise. So this is how Pareto distribution looks like. So it's more likely to sample this, but it will also sample very large values, but with lower probability. But nevertheless, the probability is not 0. The probability still exists. Okay, so what we will be looking at, let me delete this cell, we don't require this cell. So what we will be looking at is we're gonna sample from the Pareto distribution and we're gonna find the mean and variance. So I've set the Pareto distribution like this, but before that, let us just look at how the increasing distribution looks like, meaning earlier distributions were two-sided. They were symmetric about the origin, half probability to go to the right, half probability to go to the left. But in the Pareto distribution, it's obviously going from m to infinity. So either we can reflect the distribution and multiply it by -1. That's one way. But we can alternately define the random walk to only go in one direction in space. So let me make it from 0 to square root of 12 and find out why this square root of 12 comes into the picture. Let's run this and see what goes on. So the variance increases linearly in time and the mean also increases linearly in time. Why does the mean increase linearly in time? Because obviously we have steps which are only positive and hence the mean also increases linearly in time. Fine. Now what happens with the Pareto distribution? So let me get rid of this. Let me do this. And something very weird happens. We have very large values of x. Let me set the limit. Okay, so everything blows off. Why does everything blow off? Let us have a look at a few trajectories. So did we delete the trajectory code? Okay, we deleted the trajectory code, but no, never mind. We can again plot that. So we have x all values. So for j in np dot a range 0 to 10, we're gonna plot x all columns of the jth row. And this will give me the trajectories of the different particles. Let's see. So what do we see over here? We see, and okay, we have small increment, but boom, suddenly we have a large jump. It is because while most of the steps are quite small because of the nature of the choice of step from the Pareto distribution, there will be a few jumps now and then which will make a large increase in the number. And you can imagine that because of the presence of this um, far off jumps, okay, these jumps happen now and then. The jumps are not frequent because we are sampling it from a distribution in which the large jump is not probable, but it is probable, but it is not likely to come very frequently, and that is why we'll have jumps like this. And because of this, once you try to find out the mean, it will start blowing up because there will be many trajectories which have such a large jump because they might have happened sometime earlier in the simulation, or they may happen sometime in the future. But Such jumps do exist, and hence it is not easy to define. But nevertheless, what we can do is find out the PDF of the locations that may give us some insight. So let me grab this particular program and let me see how. Let us forget about the mean and variance, because for such cases it doesn't really make sense. Let me plot the PDF. Let me get rid of this as well. Let me run this. Let me set. ah, Okay, so this is how the distributions look like. They're increasing in, so the mean is going shifting towards the right. That's fine. But at the same time, we have a flat tail. So the tail is not really coming down like a Gaussian. It's sort of extending all the way to infinity. Well, and that is called as a fat tail. And it should be clearer if we do a log plot. So if we double log everything, we should be able to see the existence of that power law. Okay, so that power law does exist. In fact, let me get rid of this limit to highlight that power law. So this is that power law. Okay, so this long tail that exists, it never goes to zero. But now, who said that this is that fat tail? I mean, I've not shown you how the Gaussian distribution looks like in the log. So let's do that. The normal distribution, how it looks in log. So the beauty of reusing a code is you can just change the return value and you can get the distribution you want, and boom, for a Gaussian always comes down quickly. It does not have that power law decay. All right. So yeah, these kind of walks are called as Lévy walks. It is named after French mathematician Lévy, whose work on all these kinds of fat tails gave rise to distributions called as Lévy stable distributions. And such kind of catastrophic jumps are quite common in groundwater transport. So, for example, if you have a porous medium, in the porous medium, you have regions of high hydraulic conductivity, low hydraulic conductivity. So, if a particle is going like this, if the conductivity is high over here, its position will suddenly increase. But if you have some, it keeps on going. If it encounters a region of high conductivity, again it will suddenly increase. Okay, so such kind of paradigms are quite useful to model various kinds of physical processes. It's not just for fun that people do this, and all this fall within the domain of stochastic modeling. It has also ramifications in finance and choices, a lot of economic planning and things like that. But I have shown you some of the tools with which you can get started already. Well, what we have done is we have only discussed with the step size distribution, whereas we have kept the time distribution to be fixed. Each time we are doing a loop over delta t. Alternately, you could have a distribution of times as well. So we could have a distribution of waiting times. It is meaning that if a particle is going like this, it will wait over here for a long time before making another step. It will wait over here for a long time before going to somewhere else. So such kinds of waiting time distributions are quite useful for queuing theory. Whatever. It's quite a doozy spelling. So queuing theory, it's quite important because in order to understand how your industrial process should be or how a queue should function, you must understand what waiting times distribution will you will have if you have so many processes downstream or upstream. And uh, such kinds of stochastic processes in which there is a distribution of waiting times. They are called as CTRWs, that is continuous time random walks. Okay, and continuous time random walks are also very important from the point of view of modeling hydrological flows. So how a solute will wait in a region of low conductivity or it will not wait in a region of high conductivity. So the distribution of velocities and over the entire domain gives rise to such kinds of wait times, which eventually allow us to look deeply into how the dispersion of a solvent or a solute in a given porous medium will happen. So with this, I end this session. I hope you enjoyed this. I hope you will take away many wonderful things from this particular set of examples that we did. You can try doing this kind of random walk for a bunch of different distributions of step size, time, or even do it for a host of uh, step distribution functions which have finite variances, which do not have finite variances, and then just see what kind of things you get. For those of you who are mathematically inclined, you can have a look at a variety of books which deal with first passage times and so on, central limit theorems, and you can peer deeply into the mathematics of it as well. With this, I'm going to end this particular lecture and see you next time. Bye.